Hello again and welcome to the pre-lab lecture video series at York College of Pennsylvania. This is the video for the kinetics of a crystal violet reaction, part of the Gen.Chem 2 sequence here at York College of Pennsylvania. In today's video we're going to walk through some of the important steps in the procedure that we're going to use to derive the rate law of a reaction. So rate laws are part of the terminology of kinetics, and every reaction has a law, an equation that describes how rapidly it's occurring. In today's reaction, we're going to see crystal violet, which I'm just going to approximate as CV. It's a dye compound with a deep purple color. That'll be key to our work in the lab today. Reacting with hydroxide ions. We'll bring those in from sodium hydroxide. And this forms a product over here. We're not super concerned about what that product is, so I'll just generically refer to it as the product. The rate of this reaction, how rapidly it occurs, depends on a rate constant, K, and then the concentration of each of our reactants. And each of these reactants in our rate law has an order, N and M. So in order to know the rate law of our crystal violet reaction, we need to find these three missing components: the rate constant and the two respective orders of our reactants. We have to divide and conquer to accomplish this task. To get the crystal violet order, we're going to use the integrated rate laws. So our crystal violet will obey one of the patterns where either the concentration, the ln of its concentration, or 1 over the concentration will be linear versus time. But only one of these can be linear versus time. So the experimental procedure today will be pretty simple. We're going to collect data for concentration. Although it's not actually the concentration, it's the absorbance of our purple dye. We're going to use a small cuvette. I'll show you one in a moment. So it looks like this. We'll fill it up with a sample of our solution of reaction. And at the start, it will be pretty darkly colored purple. But as the reaction proceeds and we move from the reactant to the product side, our material changes. And the color will fade a little bit. And so we can use ultraviolet light. We can send ultraviolet light through this sample, and the amount of light that's absorbed is directly related to the concentration. So we can substitute for concentration the absorbance, actually. And so we're going to be looking for a pattern between the absorbance in time, or the ln of absorbance in time, and 1 over the absorbance in time. Because that absorbance scales directly with the concentration of crystal violet remaining in our reaction setup. So your data for the lab today is going to be quite simple. You're going to have 2 columns of data. You're going to have the time, which you should measure in seconds. Although if you measure it in minutes and then later on convert it to seconds, that's acceptable. But your graphs that you'll make will definitely need to be in seconds. And then the other values would be the absorbance. So the absorbance depends on the time. All right? And so you'll collect an absorbance every 3 to 5 minutes. There's no reason that it has to be exactly at 3 or exactly at 5. but you would want to record the exact time when you measure the absorbance of your sample. Then you will do some data analysis. And I've prepared a separate video screencast showing the data analysis of this, so I'll refer you to that after you've completed your experiment. But the goal would be to prepare graphs of the absorbance versus time, logarithm of absorbance versus time, and 1/, of absorbance versus time. One of those three graphs will be most linear. They'll all look fairly close, but one will be most linear. And that will give us the order of our crystal violet. Now the hydroxide is a little bit of a puzzle. To get the order of the hydroxide, we're essentially going to use the method of initial rates, or a comparison of two rates. We can approximate this entire piece, all right, as a constant, and I'll show you this in, again, the screencast for the data analysis. But by comparing two trials, we will be able to, like we've done in the method of initial rates, although it won't be exactly this way, we'll be able to divide one trial by the other, essentially. And all of this won't cancel out, but we'll get numbers, and this will allow us to figure out the value of M. And then substitution gives us the value of K. Okay? So these are the basic details. As far as the equipment that we're using today, I'm going to slide up the sash here. We're going to use a UV vis spectrometer. Let me zoom in a little bit so you can get a better view of the UV vis spectrometer. Okay. And they're hard to see, I can appreciate on the video, but these are the cuvettes that we use. You'll first mix your reaction in a beaker, stir it for a few seconds, and then you'll simply pour the reaction into one of these cuvettes, and that's it. You can leave it go for the rest of the lab. Now you'll prepare two separate reactions, so you'll need two cuvettes, and you'll need one cuvette as a blank. We have to blank out the spectrometer to tell it what is a zero absorbance. The cuvettes are placed on the inside here. There's a small chamber. The beam runs front to back in these spectrometers. These are controlled by the keypads over here. The instructions are all in your lab. And so you would take a cuvette. We normally wipe the cuvette free of fingerprints because our fingerprints contain oils and grease that would absorb some light. Put the cuvette into the holder, close the lid, and we'll simply get our readings off of the screen. So once you start your reaction, put the cuvette in here, it's ready to go. You simply need to put it in, take it out, because you might have to swap out your two cuvettes, or you may be sharing the spectrometer with another group in the lab. So be careful of handling the cuvettes so you don't spill them, but all you'll need to do once you start the reaction is take them in and out of the spectrometer. Okay, let's go through the pre-lab questions for this week's exercise. These are great practice for your homework in Kinetics, and they give you a little bit of an idea of what we're doing in the lab as well today. So the first pre-lab question says that after collecting your concentration and time data, a graph of that data is linear. This implies that this reaction is zero order. That's what you should be thinking. When concentration versus time is linear. It's a zero order reaction. The slope of this graph, any concentration versus time graph, the slope is equal to the negative of the rate constant. And then we have the y-intercept, which would be our initial concentration at time 0. So simply writing the integrated rate law for this reaction, A, our concentration at any time, is generically negative kT plus A0, the initial concentration. So we have the K from the slope, so it is negative 2.15 molar per second times T plus 0.500 molar. This is the concentration of the reactant A at any time. Right. Question 2, we have a first order process, decomposition of cyclobutane. So a first order reaction will always follow the ln of, I'm going to use Cb in my example, you should use the correct chemical formula probably, equals the ln of the initial concentration of Cb, all right, minus K and T. Very similar to the first order rate law, but with natural logarithms of the concentrations. Okay. What's the concentration after 2 minutes? We're given the K in this instance is 0.015. And so we'd like to know the concentration after 2 minutes. We plug in our initial concentration, 2.0 molar, minus 0.015, 1 over seconds, and 2 minutes would be 120 seconds. We have to match our units. This gives us a value of negative 1.107, but that's not the concentration. That's the logarithm of the concentration. So our concentration of cyclobutane would be e to the negative 1.107, or 0.331 molar. Okay. And then our third pre-lab question uses a second order reaction. All second order reactions follow the pattern that 1 over concentration is equal to 1 over the initial concentration plus kT. We're given again the half-life, or sorry, not given again. This time we're given the half-life. We want to find the half-life of the reaction. So the half-life, T1/2, the concentration of A is 1/2 the initial concentration of A. So we can use this relationship. If our initial concentration is 0.4 molar, then our A is going to be 0.2 molar. So I can plug in 0.2 molar equals 1 over 0.4 molar plus, I'm given the rate constant, 0.025, 1 over molar seconds, T 1/2. So I'm trying to find the time in this case for my initial concentration to be reduced to this value that's half its original value. Okay. This ends up giving me, when I subtract over this side, this would be 5 and this would be 2.5. So when I subtract, I'll get 2.5 equals 0.025 times T 1/2. So T 1/2 equals 100. And the unit, look carefully, of my rate constant was seconds. So the unit of my time is 100 seconds. So we have 100 seconds as the half-life of this reaction. Okay. So that works you through the 3 pre-lab questions. I know the description of the experiment's been a little bit briefer today than usual. There aren't too many safety concerns to worry about. The crystal violet, it will stain clothing if it gets onto it, so be careful about that because it is an intense purple color. But otherwise, you're handling base that is pretty diluted, so it's not too concentrated and shouldn't cause any sort of problem for you during the lab today. The procedure is pretty straightforward, and you should have a pretty successful opportunity to determine the rate law of your crystal violet. Again, after you've completed the lab, be sure to have your data ready, and you can watch the data analysis video that will describe how to take your raw data for absorbance and time and turn that into the rate law of your crystal violet reaction. Good luck in the lab, and I hope you enjoy yourself.